Hi, everybody, and welcome to the last day of hypothesis testing, an application of the central limit theorem. In this video, I just want to show you a couple of examples of how you can test whether or not a proportion is reasonable or not. Let me say up front a couple of things. First of all, I'm not totally sure how I sound like, but to myself, I sound kind of, what's the word? I sound lackluster and energy-less or something. I apologize. I've been vomiting for like 2 days straight. So I will try to put some pep in my voice here, but I might not be able to. Also, let me just acknowledge what I have acknowledged previously, which is that there are many things that I like about our book. There are some things I don't like. Chapter 5, and in particular sections 5.4 through 5.7, are not well written. Okay, they are poorly written, especially given how important this material is. So I apologize. That's why that for this particular material, I give you such long handouts. I'm trying to take the place of what the book should have in there, giving you something to reference. So the couple of examples I will show you here are also kind of long on text, and that is why, to give you something to reference when you do your homework. Okay, also, your homework is due on Wednesday, as I've said before. If you have questions on any of this, you can, of course, email me. I should be able to go to school on Tuesday, so I should be in there for office hours, etc. So if something bothers you, just let me know. Okay, so here's our first example. In 2005, the national smoking rate in the United States was 20.9%. Suppose that in 2005, some city had the same smoking rate as the national average, so 20.9%. The mayor then launched a massive public health campaign, advertisements, they upped the taxes on smoking, etc. And he did this to try to cut down on smoking in the city. So in 2008, you take a random sample of 200 adults. Of the 200, 31 of them smoke. So here's the question. Do you have strong evidence that smoking levels in that city have dropped? Okay, so this example has sort of two claims wrapped up into it. And notice I'm only answering the first one of them. So the first question you might ask is what's right here, which is, do we have evidence that smoking levels dropped? That's the problem that we will deal with here. The follow-up question, of course, is, do we have evidence that it dropped due to these measures by the mayor? Okay, so that's a question we will table for now because we don't have enough data given this question. But, if smoking rates were already falling at some rate, then maybe these little measures here actually didn't do anything because smoking rates were falling already due to other factors. Who knows? But we are going to put that table aside for now and just think about, do we have evidence based on this sampling and based on this data that smoking rates have dropped? And before I do that for you, let me just bring up the calculator here. Okay, so 31 out of 200. That's a smoking rate of 15.5% in your sample. That number is lower than 20.9%. So on the surface, you do have evidence that smoking levels dropped. The question is just, is it low enough? What's the probability you see a proportion like this given this data and given the claim of 20.9%? Okay, so let's look at that. To answer a question like this, you need a central limit theorem part 3 that deals with proportions. So let's let Pn represent the proportion of a population that have a desired characteristic when taking samples of size n. In the current example, the desired characteristic is, are you a smoker or not? Okay, but you can imagine it can be anything, Then, as long as n is large enough, the set of proportions, that variable is normally distributed, and the standard deviation is like this. So you take the proportion you expect to see and put it there, 1 minus it there, sample size there, square root. Okay, so in our particular example, we're investigating whether we've dropped from 20.9%. So our default assumption is that we're at 20.9%. Smoking levels have not changed. So given that assumption, what proportion of the population would you expect to see? Like, what's this P naught? Well, given this assumption that smoking levels haven't changed, the expected proportion is 20.9%. Notice that our sample size is 200. So what the central limit theorem part 3 is saying is that P200, the variable that measures proportions when you take a sample of size 200, that variable itself is normally distributed with an expected value like this, 0.209, standard deviation obtained from the standard deviation formula gives you 0.0288. So if the level of smoking hadn't dropped, the probability that we would see our data by chance is like this. So 15.5% or lower. So we integrate from negative infinity to 15.5%, and the answer we get is 3%. Okay. So if our significance level is 5%, we do have good evidence that smoking levels have dropped. Okay, so again, if smoking levels hadn't dropped, the probability that we would see data like ours by chance is 3%. That's pretty low. Okay, so here is a problem for you to try. If we were in class, you would just try this in front of me for 5 minutes or so. Okay, sorry, my kid needs to, well, just 1 second, sweetheart. Let me tell my kid goodnight here. Pause this. All right, so my kid's in bed now. Okay, so here's an example that we would do in class. So according to the Centers for Disease Control, the percentage of adults 20 years of age and over in the U.S. who are overweight is 69%. The city council of this make-believe city believes that the rate of overweight adults in their city is less than the national average. In order to test that claim, they take a random sample of 150 adults and find that 96 of them are overweight. Do they have good evidence that their city's rate is actually lower than the national average? So to get a handle on what this question is asking you, 96 out of 150, that's 64%, okay? 64% is lower than 69%. So if you just take that data point, I suppose you could say, well, yeah, I mean, it's lower in the sample, so we have evidence. But I have the answer here. If you work through the probability of seeing data like that, assuming the city rate is 69%, you get a probability of about 10%, okay? And that's not low enough to claim that we have good evidence. So in this case, you would conclude that you don't have any good evidence that you're lower than the national average. Okay, so let me just show you one more example here. Okay, so the polio vaccine was first tested in 1954 in what was at the time one of the largest clinical trials ever run. 400,000 kids took part in the trial. So that's a humongous sample size. The children were randomly divided into 2 groups of equal size, a treatment group and a control group. The control group received placebo injections. So it was not a vaccine, it was simply a saline solution or something. 57 kids in the treatment group went on to get polio. 142 kids in the control group went on to contract polio. So we want to claim the vaccine is effective, I suppose, right? Do we have any evidence of that? So before I investigate this claim here, that the vaccine is effective, I first want to point out this situation is different from the question that we just did. In this question here, we are just comparing, where is it? We're comparing a single proportion, 31 out of 200. We're comparing that proportion to 20.9%. So a single proportion relative to some baseline here. In this question here, we actually have 2 proportions going on. We have a proportion of treatment kids who got polio and a proportion of control group kids who got polio. So we need some sort of way of thinking through, these proportions are different, right? So 142 out of 200,000 is different from 57 out of 200,000. So how could we measure the probability of seeing a difference like that? So this proportion here, that's 142 out of 200,000, that's more than double the proportion you get from the 57 out of 200,000. Okay, so to measure different proportions, when you have multiple proportions running around, you need a muscled up version of the central limit theorem, more muscular than what we just did. So it takes a bit more setup here, but the example will make it clear what's going on. So let's let N1 denote the size of population 1, N2 denote the size of population 2. So in questions like this, you always have two populations of interest. In the example we are dealing with now, the two populations are the treatment group and the control group. So let's let Y1 denote the number of successes in population 1, and Y2 denote the number of successes in population 2, where in this case, we use success in quotes because in this case, a success is getting polio. It's getting this characteristic that you're interested in. Okay, so let's let P denote the total number of successes divided by the total population size. Yeah, so P is the, why is there blue still on my screen? Oh well. So P is the proportion of overall successes in the entire population. So for sufficiently large N1 and N2, this random variable right here, the difference between the two proportions of interest, okay, that difference is approximately normally distributed with this standard deviation. So the standard deviation now is you take this proportion of total successes in the population, 1 minus that, 1 divided by population of, size of population 1, plus 1 over size of population 2, and it's all square rooted. Okay, so this difference of proportions has this standard deviation, and it has this expected value, just the expected values of the individual variables subtracted. Okay, so all of that to say, what's really going on in this example? What's going on is that you have two different proportions going on. You have a proportion of polio kids in the treatment group and a proportion of polio kids in the control group. You want to compare those two proportions, don't you? So to compare them, one way you could think about that is to just take their difference and see how far it is from 0. Okay? Because what if the vaccine were not effective? If the vaccine were not effective, you would expect, where is it? You would expect this variable right here to have expected value 0 if there's no effect. Okay, so let's walk through plugging all the numbers into this example here. So we had 400,000 kids that we put into two groups of equal size. So N1 and N2 are 200,000. P1 is the proportion of the treatment group that contracts polio, and P2 represents the proportion of control group that contracts polio. Okay, so 57 kids from group 1, 142 from group 2, so we have 199 total successes, and the total population size is 400,000. So that P number from up here, this guy, is 0.0004957 or so. Okay, well, what if the vaccine weren't effective? Since the populations are so large here, we can assume that P1 minus P2 is normally distributed with expected value 0. Okay, if the vaccine is not effective, then on average, P1 will equal P2, right? If the vaccine were basically a placebo or something, just a sugar pill or whatever, there shouldn't really be a difference between being treated and being in the control group. So if P1 equals P2 on average, then P1 minus P2 would have expected value 0. And the standard deviation is this guy, using this formula up here. Okay, so if the vaccine weren't effective, we expect to see a value of 0 for P1 minus P2. What we actually see is this difference, right? Here's the treatment group proportion minus control group proportion, and this is what you see instead of 0. So what's the probability of seeing a number like that by chance? Well, it's less than what we expect, so we go from negative infinity up to it. Normal distribution stuff here, right? Everything's just plugged right in. And what you get is something really tiny. Okay, it's on the order of 10 to the negative 10th. So if the vaccine weren't effective, the probability of seeing a difference in proportions like this, simply due to chance variations, is really small. Okay, it's way less than 1%. So we have strong evidence that the vaccine actually has some effectiveness. Now, of course, the vaccine is not perfect. We did have 57 vaccine kids get polio, but we weren't claiming, or we weren't testing the claim that the vaccine was perfect. we were testing the claim that the vaccine had some effectiveness. Okay, so in your homework, you have examples that are basically just like these two. So you have, you have questions where you are comparing two different proportions to each other, in which case you want to set up a variable like this P1 minus P2 guy. If the proportions are supposed to be the same, so we had no effect of a vaccine or something, then you have this standard deviation and you have an expected value of 0. Or you can see things like this, just a single rate that you're comparing to some sort of baseline and seeing if it's bigger or lower than it should be. Okay, so for this example here, I gave you a sample problem to do and gave you an answer. For this example here, I just didn't have room on the page here, but if you go on Moodle into the daily problems section, you will see a problem like this with an answer included, so you can test whether or not you understand this process. So on Wednesday, the first thing I would do is just ask you if you are comfortable with this material or not. If you're not comfortable with it, then just ask questions. Okay, and again, I'm sorry I can't be there tomorrow. So I will see some of you on Tuesday and the rest of you on Wednesday.